Hello everyone. Hopefully you have your note packet in front of you and you're enjoying the week off between semester breaks. And we are going to get started on chapter 7, which is the second chapter of our probability unit. And basically here we go. So this chapter is all about two different types of random variables, discrete and continuous random variables. And as you can see here on this little slide, it gives you an example of what I mean when I say discrete variables versus continuous variables. So you can see the examples on the left are all discrete variables. They are numbers that can be counted, as opposed to continuous variables, which would include all the decimals and everything in between. So you can't just do 1, 2, 3. It also include 1.01, 1.001, 1. Basically everything in between 1 and 2, and so on. That's the difference between a discrete and a continuous. So, definitions: random variables. A random variable is a variable whose value is a numerical outcome of a random phenomenon. So the key word, notice it happens 3 times on the slide, randomness. So a random variable, again, is a variable whose value is a numerical outcome of some random phenomenon. So for example, if you flip 3 coins and you let x represent the number of heads, then x would be the random variable. Usually, notationally, we use capital letters to denote random variables. So when you see a capital letter, we're talking about some variable that has an element of randomness to it. The sample space, again a capital S, would list all the possible values of a random variable x. Now, there's 2 different types of random variables, as the very first slide said. There are discrete random variables, which we'll talk about first. A discrete random variable has a countable number of possible values. So for example, the coin flips. The coin flips would be a discrete random variable because you can either have 0 heads, 1 head, 2 heads, or 3 heads if you're flipping 3 coins. When you have a random variable, you like to organize your data in some way. The way we organize our data is with something called a probability distribution. So a probability distribution of x is a listing of the values of x, so in the case of the coins, 1 head, 2 heads, 3 heads, 0 heads, and the probability of each thing. These probabilities, there's 2 key elements for a probability distribution. All probability distributions have these same 2 requirements. First, every probability has to be between 0 and 1, and secondly, the sum of the probabilities must equal 1. So here's an example of a probability distribution. If we want to flip a coin, flipping 4 coins, we want to count the number of heads. We would make a listing like this. So you can see the listing, the sample space up above, up here, that has all the different coin tosses, and then x, 0 heads, 1 head, 2 heads, 3 heads, 4 heads, and you can write this on your paper. And then underneath there, you have to have the probabilities. You have to include the probabilities for each one. So the probability of 0 would be 1 out of 16, 1 is 4 out of 16, 6 out of 16, 4 out of 16, and then again 1 out of 16, and notice that if you add them all up, sure enough they equal 16 out of 16, which is 1. You can also show using a histogram. So we have the same idea behind this one. If we toss 2 die and we want to make a distribution of this, what we would do is we would make a listing of how many ways each thing can happen. So you can get a sum of 2, right? The x is the sum, in one way. You can get a 1 and a 1. So there's 1 way out of 36. And a 3 would be 2 out of 36. And a 4 is, well, let's think about the ways that we can get a 4. We can get a 4 with a 1 and a 3, or a 3 and a 1, or a 2 and a 2. Right? So there's 3 ways for that. So 3 out of 36. And then a 5 would be a 1 and a 4, or a 4 and a 1, a 2 and a 3, or a 3 and a 2, or that's it. So 4 out of 36. And so on. So you can continue this list, and I would encourage you to go ahead and continue this list and go on through and complete the probability distribution. So it should all of them be out of 36, and they should all add up to 36 out of 36. Once you have that probability distribution written in this format, then you could turn that into a probability histogram. And so you can see the way this works out. So this is a sum of 2, there's one way, and this is just doing a count. So instead of having probability on this side, we're just counting. There's one way to get a sum of 2. There's 2 ways to get a sum of 3. There's 3 ways to get a sum of 4, and so on, and so on, and so on. So you can see it makes a nice, neat, symmetric distribution when we're talking about tossing coins. That leads us then into the second type of random variable, which is a continuous random variable. A continuous random variable takes on all the values in an interval of numbers. So it would include not just 1 head, 2 heads, 3 heads, but everything in between, including all the decimals. A probability distribution of x can't really do a histogram in this case because it's not countable. Instead, it's a density curve. So you have to remember back when we studied normal densities, normal distributions, what a density curve looks like. Remember that with a density curve, the probability of any event is the area underneath the density curve and above the values of x that make up that event. So I'll give you an example. So remember this from the third chapter a while back when we were doing density curves. If we have a density curve that looks like this, so it had a height of 1, the probability that this occurs between 0.3 and 0.7, that x occurs between 0.3 and 0.7, would be the area underneath this. So the total area of this curve, well, it's 1 wide by 1 tall, so the total area is 1, so then the area between 0.3 and 0.7 is 0.4. So the probability then is 0.4. This is an example of a density curve. So remember, density curves must be above the x-axis, and the area underneath them has to add up to 1. So normal distributions are probability distributions. Probability, when we were studying normal distributions back in the first semester, we were studying probability distributions and we didn't even know it. So I would have you remember this formula that if x has the normal distribution with a mean of mu and a standard deviation of sigma, remember that's what these little symbols here next to the n stand for, is the mean, mu, and then standard deviation sigma. Then the standardized variable, the z-score, is given by that formula. And it has a standard normal variable, has a distribution, a normal distribution, that's what the capital N means, with a mean of 0 and a standard deviation of 1. So the advantage to using these z-scores, if you remember, is it allows you to take two different distributions that don't have the same mean, that don't have the same standard deviation, and allows you to compare them in a standardized format where they both would. We could convert them into the standard normal variable, and then we'd be able to compare them to each other using the z-scores. Okay, here's another definition. If we have random variables and we want to find the mean of random variables, so to find the mean of x, what you do is you multiply each value by its probability and then add the products. This is also called an expected value, so you should highlight that word, expected value, because you'll hear me use that a lot. Right now I'm just asking you to write down the formulas so that you will have them to refer back to, and when we come into class, the next time you're in class, we will be doing a lot more of these concrete examples and calculating expected values. So here is one example to give you an idea. The Michigan Daily Game is you pick a 3-digit number and you win $500 if your number matches the numbers drawn. The question is, what is the average winnings? So what you would do is you were calculating the average, the mean, of the random variable x. The probability is 0.1% that you win $500. And 990 basically is 1 out of 1,000 because it's a 3-digit number. So 1 out of 1,000 that you win, 999 out of 1,000 that you lose. So the probability you win is 0.001, probability you lose is 0.999, multiply times the expected winnings, and you can see that the expected winnings would be 50 cents. That's why they charge you $1, because that way Michigan gets $1, is expected to get $1 on every ticket. 50 cent net on every ticket. So if the Michigan Daily Game is you pick a 3-digit number and you win, what's the average profit? Well, I kind of just hinted at that. So in Michigan, if you're playing this game, you're going to spend $1, and if you win, that means you take home $499. So your profit in that case is $499. If you lose, well, then it costs you $1, and that's why it's -1. So multiply all that together, and you can see that playing a game is a losing proposition over the long term. You are expected to lose 50 cents every time you play. So you're just throwing your money away, basically, to play this game. In the short run, yes, possibly you could win. In the short run, it's conceivable you could play 3 times in a row and win every single time. It's not very likely, but it is possible. But in the long term, Michigan wins. The state of Michigan wins because they know that over however many millions of these tickets they sell, the average is -0.50, so they're going to make money. This is called the law of large numbers. If you draw independent observations at random from any population with a finite mean mu, meaning something not infinite, it actually has a concrete mean, decide how accurately you would like to estimate that mean, and as the number of observations drawn increases, the mean x bar of the observed values will eventually approach the mean mu of the population as closely as you specified, and then will stay that close. It will never get any farther away than that. So basically it's saying is that if I'm playing the Michigan game and I buy 3 tickets and I win all 3, well, my average winnings are $500. But if I were to play 10,000 times, the law of large numbers says that ultimately my mean is going to become very close to the population's mean, and the population's mean was 50 cents. So even though I started out winning 3 times in a row, if I play enough times, my average is going to become very, very close to the population's average. So here's another example. The distribution of the heights of all young women is close to the normal distribution, with a mean of 64.5 inches and a standard deviation of 2.5 inches. What happens if you make larger and larger samples? So here's an example. If I'm only doing a couple of observations, if I'm only doing 1 to 5 to 10, even 25 observations, the average can be very low. After 10 observations, the average is 63.5, which is almost a whole inch less than what you would expect. And after it looks like about 25, the mean's down at 63. But as the number of observations gets closer and closer and closer, gets bigger and bigger and bigger and bigger, then the observations mean, the sample mean, will get very, very close to the population mean. And so you can see that after 10,000 observations, my sample mean, my 10,000 sample mean is very, very close to the population mean, which we know is 64.5. Some people will then incorrectly believe that there is a law of small numbers, and that's just totally not true. There is no law of small numbers. Even though you can flip a coin and you can get heads 10 times in a row, that happens, that's randomness, that does not equate to some sort of law of small numbers. Okay, so here's another formula for you to write down. If we know, or if we're given, that mu is the mean of x, then the variance of x is given by this big long formula. Right? So you want to write that down. And you should recognize, hopefully you remember, that the variance is the standard deviation. The standard deviation of x is the square root of the variance. So you must first calculate the variance, and then once you've calculated the variance, if you take the square root of that, that gives you the standard deviation. All right. So let's take a look at an example, back to our Michigan Daily game. If we pick a 3-digit number and win $500 every time the number matches, what is our average winnings? Remember this? If we wanted to calculate the variance, then here's what you would do. You would do 500 for your winnings minus the 50 cents, which is your average, square it times the probability. Plus, the other option is that you don't win at all, which is 0 minus the average winnings, square it times the other probability. Do a little bit of math, use your calculator, let your fingers do the walking, and there's your answer. So your variance is 249.75, and your standard deviation is 15.8, because you have to take the square root in order to get the standard deviation. All right, so hopefully What I would like for you to have written down on your paper is the big long formula for the variance, and then next to it write this example. And this is a real simple example because there's only two options. You either win or you lose. When we come into class tomorrow, we'll do some more examples that are a little bit more complicated. But at least this way you have the formula in front of you and you're ready to go for that. Okay, there are two rules for means. If you're trying to find the mean and you have this situation, a plus bx, that's the same thing as a plus b times the mean of x. Rule 1 says the same scale change of elements of a probability distribution will have the same effect on the means. So if I'm scaling up, or if I'm changing the elements of the distribution in some way, in this case I'm multiplying the random variables times some letter b and I'm adding some letter a, it'll have the same effect on the sample mean. If I have two separate variables, rule number 2 is if I have two distributions and I want to find the sum of both distributions, then I just sum the means, right? So if I have two, the mu of x plus y is the same thing as the mu of x plus the mu of y. Okay, so here's an example to illustrate these two rules. A company believes the sales of products X is as follows. So they believe that they will sell 1,000. The probability that they sell 1,000 of these items is 0.1. That they'll sell 3,000 of these items is 0.3. 5,000 is 0.4, and 10,000 is 0.2. Right? That adds up to 100%, which is what we would expect. If we were to calculate the expected value, X is 1,000. Probability is 10%, so we multiply those together. 3,000 times 0.3, 5,000 times 0.4, 10,000 times 0.2. Add them all up, we get 5,000. So this company would have an expected number of units of 5,000 units being sold. If the expected profit on each sale of product X is 2,000, then what would be the overall expected profit? Well, they're expecting to sell 5,000 of them. The expected profit is $2,000 per item, so this would be the rule number 1. We can use rule number 1 to help us figure out that the expected profit would be $10 million in this case. Okay, so rule number 1, there's a good example to illustrate rule number 1. Okay, another rule for number 1 examples. Different company. They're selling our same company. This time they're selling a different product. It's not as popular as the first product. They're not going to sell as many of it. You can see the different distribution. So they're expecting a 40% probability they sell 300, a 50% probability they sell 500, and so on. The expected value, 300 times 0.4, plus 500 times 0.5, plus 750 times 0.1. So they would expect to sell, the average sales for this product would be 445. If the expected profit on each sale of product Y is 3,500, so product Y, they're going to make more profit, must be a more expensive item, that's why they're selling less of them, would take the 445, the average expected value that we calculated in the previous slide. They're expecting to make $3,500 per item, so we could use rule number 1 to figure out that their expected profit on this item, this product, is $1,557,500. All right, so now rule number 2. What's the total expected profits combined of both product X and product Y? So if we're going to add them together, right? So we're going to take them both. This would be rule number 2. All right, we want to find the combined products, the combined profits. So therefore we can simply add them together and we get our answer. Okay. Means have rules, variances have rules. So variances, now these only apply, only if the distributions are independent can we apply these rules, and we'll talk more about this in a little bit. But they do have to be independent distributions, otherwise these rules don't work. For variances, for means we had an a plus bx, for variances we have an a plus bx also, but it's a slightly different rule, and you can write that rule down. So if a scale change involves a multiplier b, the variance will change by the square of b. So this is the formula you want to write down. Notice that adding something to the distribution does not affect the x, but multiplying it has a big effect on it. And then rule number 2, if we're going to add them together, the variance of the sum of two distributions is equal to the sum of the variances. And if we're going to subtract them, now here's something interesting, rule 2b, even when you're subtracting the variances, you still add. So notice that x plus y and x minus y have the exact same rule. And that can be confusing, and I'm going to give you some examples of that to go over and kind of see why this happens. But you should definitely write this down, and then we're going to do an example here. So back to our daily 3 lottery. It has the following mean and the following variance. Remember, we calculated these earlier. What's the mean and the variance of the winnings? Well, the winnings is you have to subtract your dollar, because, right, you got to spend $1, so your winnings would be, for the mean, you would subtract $1 and you get negative 0.50. The variance is unaffected by the dollar, right? That's rule number 1. A plus bx, the a doesn't have any effect. So the variance, subtracting, not changed at all. The means change, but the variance is not. Okay. What would be the mean and the variance of the payouts if you were to play twice? So if you were to play twice, what happens? Well, you would have two different means, and you're playing twice, so x plus x. So means add. You can simply add 0.50 plus 0.50, so you get your mean is $1 if you play twice. Variances also add, so you would take your variance, which we calculated at 249.75, add those together. To get the standard deviation, you take the square root of that. Notice that the standard deviation up top of 15.8, you do not multiply by 2 to get the new variance when you're doing it twice, because the variance adds twice, but then the square root is how you go about getting the standard deviation. So the standard deviation up top, 15.8. At the bottom, the standard deviation is not multiplied by 2. The variance is added twice, and then you take the square root. Okay, so one more example. What's the mean and the variance if you were to play every day of the year? So every single day we're going to go about and play this. So x plus x plus x plus x. Well, that would be 365 days, so our mean is 182.5. The variance, we can do the same thing. Play 365 days, multiply them all out, and then take the square root to get the standard deviation. All right, so that's the rule for going about adding these up. Okay, so here's another example dealing with SAT scores. The verbal scores on the SAT have a normal distribution, that's what the capital N stands for, with a mean of 508 and a standard deviation of 112. The math scores have a normal distribution of 518 with a standard deviation of 114. What's the probability that a student has a combined score of above 1200? In order to answer this question, we're going to have to combine these math and verbal scores. So if the verbal scores, the X, have a normal distribution of 508, 112, the math, which is the Y, has a normal distribution of 518 and 114, the mean combined SAT score we would use would be the rules for means. So we would go about doing it this way. The mean of x plus y, the math plus the verbal, we'd add them up, so the mean is 1026. Standard deviation, here's our rules. All right, so we're going to use rule number 2. All right, so x plus y, so we would square the 112, square the 114, add those together, take the square root, that's our standard deviation. So therefore, the combined SAT scores have a mean of 1026 with a standard deviation of 159.8. Now, can we go about figuring out the probability? Well, the question we have to remember is, are all of our assumptions reasonable? Are these things independent? Are we allowed to assume that the distributions of math and verbal scores are independent? Right? And the answer is no, you're not. And the reason for that is because if you get a good score on the verbal test, you are likely to do well on the math. They are connected. If you get a bad score on the math, you are likely to get a bad score on the verbal. Everything is interconnected that way, so these two things are not independent. So I went really fast through a lot of these things. Hopefully you have all your notes written down, nicely organized with a couple of examples for each one. And when you come to class tomorrow, we'll be able to start doing some practice problems and getting ready for the end of chapter quiz. So have a good evening, and I will see you next time.